Okay, thank you very much for inviting me. My name is Woosok. I'm working in Nordita and Department of Mathematics in Stockholm University. So today I'm going to introduce a very simple tool which everybody could understand, but hopefully useful for the analysis of a monthly climate data. So simply, I'm going to introduce a very simple stochastic model to represent the statistics of monthly climate data. So, okay. So I think everybody in this room is familiar with this concept. So, the Brownian motion. So Brownian motion is just a, random motion, and then obeying some, Gaussian statistics. The most useful equation is called OU process, so which is represented by this Langevin equation. The physical implication is if there is a big particle, and then this big particle could be, collided by a lot of small particles, and then we want to represent the, the motion of this big particle statistically. But in the case we can write down one, stochastic differential equation for the velocity. Here is, time change of the velocity, and then this one is a kind of representing some stability drag. And the last term represents noise, that is the statistics of this collision. And then this, as you know, this one represents the red noise, and then it could be used for climate phenomena, for example, sea surface temperature. But if we go to seasonal dynamics in climate, I want to apply that concept. However, our seasonal dynamics is a little bit different because, we have external forcing, periodic forcing. It is given by, astronomical condition. The Earth is going around the sun. So this cannot be included in the dynamical system as a, internal variable. So we need a external, time-dependent term. So think about, previous figure. There is a big particle affected by small, collisions. Maybe in this context, this, small particle collision might be understood as some weather effect. On top of that, there is a quite strong periodic forcing. So because of that, if you look at any data in climate, for example, I'm quite interested in Arctic sea ice. If you look at the Arctic sea ice change for around 30 years, you cannot see any, big change right here because there is one big, periodicity right here. That's a seasonal cycle. Maybe if you look at the northern hemisphere and southern hemisphere, temperature change for 100 years, what you could see is there is one big, periodicity right here, seasonal cycle. So in our climate, seasonal cycle is the biggest one. And then, the change means this cycle is slightly updating because of some reason, maybe including global warming. And then if we go back to further, this one is bugging me. Okay. So in the case, what I want to do is I want to apply some stochastic model to represent some variation around that, seasonal cycle, which is most the dominant cycle over there. That's the purpose of this talk. So first, if you look at the original data, for example, southern and northern hemisphere average temperature for 100 years, you can see that a lot of dominant cycle. And then normally, to analyze this data, we normally take a climatological mean seasonal cycle and then take out that from the original data. In the case, we can see this kind of a variability change. So in the case, we can see that something is going on right here. That's the kind of a common way to analyze the climate data. So in this process, I want to connect this process with some models. For example, in seasonal time domain, the most important thing is energy flux balance. For example, if we think about the surface temperature, the surface energy flux balance is represented by some temperature change on the left side, the internal energy change, and then there is some fluxes. So and then I divided this fluxes by 3 terms, depending on the time scale. And the first one is just a collection of the seasonal forcing, which is periodic. And the second term is a white noise term. I want to say that that's the contribution from the weather. And the last one is very slowly varying forcing, which might contain some effect of the global warming and ocean circulation, everything. And then kind of after dividing up some factors, maybe temperature evolution equation represented like that. So here, this model should represent this situation. So I want to take out the climatological mean seasonal cycle. In this model, I argue that there is a T-bar satisfying this equation, some mean equations, okay? So T-bar is a climatological mean seasonal cycle we could calculate from the data itself. And then I'm considering about some fluctuation around the mean seasonal cycle. I'm going to call it X. This X magnitude is much smaller than this whole seasonal cycle. So in this model, I'm going to only take first Taylor expansion terms. But in the case, the model for this fluctuation might be approximated by some linear stochastic differential equation. However, the stability factor, this one, and noise amplitude might be periodic function. I'm just saying might be, okay, if it is right. So I want to apply this one to some tropical climate indexes. But in the case, I'm not going to ignore that long-term contributions. I mean, later if somebody asks, I'm going to say why, but right now, just trust me. I'm going to apply this model without long-term contributions. It's a very simple model, which is analogous to Langevin equation previously suggested. Only difference is this guy and this guy are periodic function. I mean, think about it. If we have the data X, this X is some data after erasing climatological mean seasonal cycle. But in the case, I want to construct the AT and NT out of the data. Okay, that's the proposal. So a simple way to do it, I'm going to multiply X on both sides and then take an ensemble average, right? Very simple. I mean, in the case, AT, I mean, this white noise X ensemble average is going to be 0. So because of that, AT is going to be approximated by this equation. This is just, the balance right here after multiplying X, and then take ensemble average. And then after finding AT, because we know AT, we can construct the new data, YT, like this one. If this model is correct, YT only contains this noise term. So I can calculate the noise magnitude by this relationship. So it's very straightforward. So think about it. I applied this, simple, construction in this linear 3.4 data, and then comparing with the data. So let's say that. Okay, here, this black one represents the AT, constructed from the previous equation. Okay, that AT axis is right here. And then this dashed line represents the noise amplitude. And then it is a periodic function, right? So, and then after putting this function into the previous model, and then, we can simulate that, putting the, noise every time, just to simulate that. And then let's compare it with the original, data. This is a comparison. Looks similar, but of course, at each point, the values are different because it is noise induced. However, if I compare seasonal statistics, monthly standard deviation, this is the comparison. Okay? So thick one is the original data. So linear 3.4 standard deviation, seasonal cycle of the standard deviation. This is January, February, this one is December, and then this dot is from that simple model. And then this simple model could regenerate the seasonal statistics of linear 3.4. Let's go back to the other example. This one is an Indian Ocean dipole, another index representing Indian Ocean climate variability. So this one is also AT, this one is NT, and then simulate that, and then compare with the original data. And then this is the comparison. A little bit disappointing compared to linear 3.4, however, still, this model captured the main characteristic of seasonal statistics of the data. and they're quite well matched. And then I'm going to show you another example too. This one is a Nile River discharge data. This is also monthly data. And then I just took initial 30 years data. Maybe I think a starting year 1970. This one is 1870. This one is 1900. I chose this time period because at that time there was no dam in Nile. But in the case, I can do same things. And then this blue one is 80. And then this red one is anti-noise. And then I also run it. And then compare it with the data statistics. And then this is the comparison. Blue one from the data, and red one from that simple model. So it suggests that this model could generate the seasonal statistics of climate data. And then it could be interpreted physically. Because two terms, AT and NT, has some meaning. This AT, think about it, AT is a positive means exponential growth, AT negative means exponential decay, which means it represents the stability of the system. If the AT is positive, which means that there exists a positive feedback driving that phenomena. If AT is negative, negative feedback is driving that one. I showed Nile River discharge because sometimes AT is positive. There exists some positive feedback. And also, if you look at the answer, in the AT here, you can see there exists the positive of the AT, which means there exists the positive feedback driving in the answer. We know what that is, Bjorknes feedback. So this AT actually representing the seasonal cycle of the Bjorknes feedback. So based on this model, okay, I just want to show one thing, what kind of things could be explained. So if there exists the positive feedback in some climate phenomena, that there is a time when the AT is positive, there is a time AT is negative. For example, in case of the answer, so from the summer to the winter, AT is positive, and then the rest of the time period is negative. But just to think about simply that model, exponential growth and exponential decay. And then every time noise is just forcing the system. But in the case, during this time period, all the response from the stochastic forcing, that response start to amplify and then piled up right here. Because after that, this response is going to decay out. What I want to explain is in that model, what we could see is if there is a maximum of the variability, that time is when the AT change the sign. Okay? So now if we go back, okay, good, look at the closely. I mean, if there is a positive feedback, negative feedback, positive feedback, but in the case of this phenomenon, say, variance change like that. There is a maximum right here, there is a minimum right here. And then I told you, in case of the answer, this time is winter, December. But in the case, I want to ask a question. If you want to see the abnormal cases in answer, abnormal cases answer means El Nino or La Nina. Which time is most probable? Winter, right? Because the variance is going to be maximized there because of the position of the positive feedback. I just explained a simple explanation about the seasonal phase locking of the answer. Okay? Very simply understood. So now, I want to expand this model for the two-dimensional cases. I mean, as you know, it is just one-dimensional. I just focused on one case and then apply the method. However, as you know, the climate could be connected and then influence each other. So I just want to expand this model to make some network model. So it is just a preliminary. And then I chose two phenomena in tropics. So Nino and IOD. So I want to connect these two. So initially, if you look at the equation, this part is the same as before, but I include a simple coupling terms between the two. Okay? Two coupling terms exist. This coupling coefficient is also periodic function, because seasonally, that coupling should be different. So the meaning is here, this guy, B12, is the influence of IOD to a linear answer. And the B21 meaning is influence of linear to IOD. Should be different, as you guess. And then how to construct it? I mean, very simple. Again, multiplying eta 1 and eta 2, and then take, ensemble average. I'm not going to show the detail. It's just algebra. You can find all of the coefficient using, data statistics. And then I'm going to show the result. So, for example, I'm not going to go into the detail. This red one is important. This red one is B12. The physical meaning is influence of IOD, Indian Ocean, to the answer. This guy, this red one, represents the influence of the answer to IOD. You can see the asymmetry. Here, quite negligible compared to other stability terms. But here, the influence of the answer, this coupling term, is quite compatible with other terms. Which means if there is answer and IOD, answer is influencing IOD quite a lot seasonally. But IOD, the answer does not get many influence from the IOD. So these two coupling functions could tell us what kind of impact are exchanging between two phenomena. So, okay, that's the last slide. And then, this is a kind of a comparison. I mean, that two-dimensional model could be simulated simply, okay, putting the noise, two equations every time. And then this one is a kind of a linear 3.4, and then simulation, looks similar. And then this one is IOD, and then simulation. And then this one is a comparison of the standard deviation of the answer. And then always, blue one is from the data, and red one from the model. And then this one is IOD. And then this one is covariance between answer and IOD. So this blue is from the data. I calculate that. And then red one is from the simple model. So this simple periodic linear stochastic model could represent the monthly statistics contained in the data quite well. So in the future, I want to expand this one to make a proper network model in tropics for seasonal predictions, because it's quantitatively quite good. Thank you very much.
Very nice talk. I just want to ask, can you comment a little bit more about how you calculate the coefficients? What is the length of your training data? Or do you use all the data? Or
I think it is important thing is that we have to make a statistics of standard deviation or correlation between two adjusted months. So in the case, accuracy is dependent on size of the sample. So normally I use several decades, like 30 years, more than 30 years. To calculate these statistics, 30 years means I use 30 samples. But 10 might be small, right? But for linear 3.4 and IOD index, I used 100 years sample to calculate that coefficient, that function, AT and NT. But for Nile River discharge, I use 30 years. Because this ongoing research, I just want to see the positive feedback for the flooding of the Nile River. But in the case, I should find a time period when the dam was not constructed over there. But at the time, 1902, the dam was constructed by UK. So. Sorry? Can you
say something about the asymptotic stability of the system?
The asymptotic, you mean the AT?
Yeah.
That's what you mean, asymptotic stability? Okay, I want to call it seasonal stability of the system, okay? So what do you want to know? I'm not sure about your question.
I guess you can characterize asymptotic stability.
Yes, I think so. So I'm still confusing about the, the meaning of asymptotic stability. What do you mean by that? Huh? I mean, long-time simulation is definitely, it could just converge it to periodic, periodic stationarity. So kind of the PDF is going to be generated every month, and then that one shows the, the periodic solutions, but that one is continuous. Okay, it is not just one point, convergence or one, PDF, because it is a coefficient is time dependent. Because of that, the long time behavior is a seasonal cycle of the probability density function. I mean, that one can be easily calculated.
Right. I'm tempted to ask more, but we have to move on. So thank you very much. And let's welcome our next speaker.